In this video I will go through the GCSE Chemistry 2019 Unit 2 paper. So question 1 is about the blast furnace, and the main ore from which iron is extracted is hematite. Part 2, redox. Well, it's made up of two words, reduction and oxidation. So a redox reaction is one in which reduction and oxidation occur at the same time or in the same reaction. B. Part 1. The reducing agent in the blast furnace is carbon monoxide, and it is made in two steps. So the first step is carbon from the coke reacts with oxygen in the hot air to form carbon dioxide, which then reacts with more carbon from the coke to form carbon monoxide. Now it needs to be balanced, so we'll have to put a 2 in front of the CO on the right hand side. Then some might say it's the main equation in the blast furnace. This is the actual production of the iron. So we've got iron 3 oxide, which is Fe2O3. It reacts with carbon monoxide, so that would be 1 mark. The iron 3 oxide gets reduced to iron, and then the oxygen goes to the carbon monoxide and forms carbon dioxide, so the right hand side is worth a mark. If you've got 2 marks, then you can get a 3rd mark by balancing it. So we need a 3 in front of the carbon monoxide, a 2 in front of the iron, and a 3 in front of the carbon dioxide. So you can see that the iron dioxide has been reduced. It loses oxygen, and the loss of oxygen is reduction. And the carbon monoxide gains oxygen going to carbon dioxide, and oxidation is the gain of oxygen. So this is a redox reaction because reduction and oxidation are occurring at the same time. On to part C then, about phytomining. Now there are only 2 marks because we just have to explain how a solution of copper 2 ions is formed from the plants. So the first thing that happens, obviously the copper that's in the soil gets taken in through the roots and up to the leaves, and the plants then get burnt to an ash, and then sulfuric acid is added to that ash. Now it could be any acid, for example like hydrochloric, but sulfuric acid is the one that's usually stated because it forms a solution of copper 2 sulfate. To part 2 then, so why can iron displace copper from the solution? Remember, scrap iron is used, so that it uses up a lot of scrap iron, and the reason this works ties in with the reactivity series. So you imagine metals like potassium, sodium are way up at the top, and as you go down you've got iron, and down towards the bottom you've got copper. So you can see that iron is higher in the reactivity series than copper, which means it is more reactive than copper. And don't just write iron is more reactive, you have to say than copper. You could also say iron is higher in the reactivity series than copper. Part 3 then is a half equation. Now half equations always include E minus somewhere, either in the left or in the right hand side of the equation. So we want to show the formation of copper. So the copper is going to go on the right hand side. It's formed, and it's formed from copper 2 ions. So the copper 2 ions need to go on the left. Now remember I said E minus has to go somewhere in a half equation always. Well, on the left it's Cu2 plus, and on the right the copper is neutral. So that means that the copper 2 ions must have gained 2 electrons to form the copper atoms. And part 4, an advantage of phytomining over traditional methods. Don't say things like less pollution, that's too vague. So you need to state something like less noise pollution or less dust pollution. It also uses up scrap iron. So those are just a couple. I mean, you could also say It avoids the removal of large amounts of rock. Energy is produced when the plants are burned, etc. Question 2 then is asking us to explain how a catalyst works. So it's not a definition of a catalyst, which is a substance that speeds up a reaction without getting used up. So how does it speed it up? Well, it lowers the activation energy and it provides an alternative route for the reaction to occur. So if you think of your energy level diagram, so we've got energy up here and then the progress of the reaction. Reactants, let's say products, this is just an example. The reactants have to have a certain amount of energy before they, if you like, tip over, before they proceed and turn into products. If they don't have enough energy, then they just bounce off each other and nothing happens. And this energy is known as the activation energy. So this, if you like, is the route that this particular reaction is taking. But when we add a catalyst, it provides an alternative reaction pathway. And now you can see it has lower activation energy. The activation energy always goes from the reactants up to the top of that peak. So the answer then to this question is that a catalyst provides an alternative reaction pathway of lower activation energy. Now, do make sure that you have reaction pathway in there. Don't just write provides an alternative pathway. The reaction is a key word to have. B part 1, dynamic equilibrium is a definition, which you just have to sit and learn. That's where the rate of the forward and reverse reactions are the same, and the amounts of reactants and products remain constant. So just be careful about how you word this. In the second part, the amount or the concentrations of the reactant and products remain constant. Do not say that they stay the same or that they are equal, because they're not. And when you increase the temperature, the rate of the reaction increases. That would be 1 mark. And then another 3 marks for 3 points explaining how increasing the temperature increases the rate. Well, particles gain energy, and this leads to more successful collisions per unit time. Part 3. Now, Le Chatelier's principle has to do with systems in equilibrium. And it states that when a system in equilibrium is exposed or subjected to a change, the system will change or move to try and establish the equilibrium. So I'll write out the equation again for the production of ammonia, just so we can see the reaction that's taking place. So we have to explain the effect of pressure on the yield. This has nothing to do with rate. Okay, so sometimes equilibrium questions and a rate question are put together. So just be careful you don't get them mixed up. So it's nothing to do with the rate of reaction. Now the yield in this particular reaction will increase. And the reason for that is because there are more moles of gas molecules on the left hand side, and increasing pressure always moves the equilibrium to the side with fewer moles of gas. So here you can see on the left hand side I've got 1 mole and 3 moles, so we have a total of 4 moles of gas on the left and 2 moles of gas on the right. So you increase the pressure, equilibrium is going to move to the right. So this is a way of writing it. The equilibrium moves to the right or shifts to the right, to the side with fewer moles of gas, and put in gas. It's not just to the side with fewer moles. Okay, so pressure only deals with gaseous molecules. See part 1. We have to explain in terms of bonds why this is an exothermic reaction. Well, when bonds are broken on the left-hand side, and bonds are always broken on the left-hand side, the reactant side, that requires an input of energy, so that's endothermic. Bonds are made on the right-hand side, and when bonds are made, that releases energy, so that's exothermic. If this reaction is exothermic, which we're told it is, then it means that the energy given out when the bonds are made must be greater than the energy required to break the bonds. There are 3 marks for this, so this is one way of answering the question. So I'm going to say the energy required to break bonds, and you have to state the names of the reactants and the products. So don't just say the energy required to break bonds or the energy required to break bonds in the reactants. Give the names of the reactants or the formula. So the energy required to break bonds in nitrogen and hydrogen is less the energy released when bonds are made. And again, just state the name or the formula of the product. So in this case, in ammonia or in NH3. Do just be careful when you're saying this, because sometimes people write the energy required when bonds are made, and so they'll lose a mark. Remember, energy is only required to break the bond, but energy is released when bonds are made. So another way you could have answered this is by saying that the energy released when the bonds are made is more than the energy required to break the bonds. And then part 2, complete this reaction profile diagram as exothermic. So that means the products have less energy than the reactants, because the reactants have given out energy. So I'm going to start off and put a line that's below the reactants, and this is for the ammonia. Reaction profiles always have this sort of hill or hump which goes from the reactants line to the products line. Now it says include the energy level for the products. Okay, I've just done that. And the energy change. So we have to show that this is an exothermic reaction. This is where the energy started. Okay, so the energy always starts at the reactants, and it now goes down to the product side. And you can see that that energy change, so I'm just going to label delta H, you could say energy change, it's going down, so it's negative. And that's how we recognize an exothermic reaction. It has a negative value. If the arrow from the reactants to the products had gone up, so let's say, for example, it was this way around. So here we had the reactants and the products. Now you can see that the energy change has gone up. That's a positive value. So the energy change is endothermic. But over here, it's going down, negative, it's exothermic. Now I have to calculate the energy change from bond energies. Again, I'm just going to write out the equation. And it can be a good idea to show all of the bonds that are involved here. So we have 1 mole of nitrogen. So that's just one N triple bond N that gets broken. And then we've got 3 hydrogen molecules. So it's clear now that we have 3 times 436 in terms of the energy that's required to break all of those bonds. And then on the right hand side, now ammonia is NH3. But we have two of those, so we have to multiply this by 2. So again, if I just draw it out like this, you can see that there's 1, 2, 3, 4, 5, 6 NH bonds that have to be broken. And again, just drawing it out like this can make it clear as to what's happening. Now I've got that done, I can work out the bonds broken, or the energy required for the bonds broken, and the energy released when the bonds are made. So that's 2, 2, 2, 4. And then I work out the energies released when the bonds are made. So again, there are, as you can see, there are 6 NH bonds. So that equals 2, 3, 1, 6. When to work out the energy change, it's the bonds broken minus the bonds made. So that works out to be minus 92 kilojoules. Now the sign in front of the answer is very important. Obviously in this case it does work out to be minus 92, but if the value had been a positive value, to say plus 92, you would have to have put the plus in front of it. You wouldn't just have written 92. So when you're doing calculations involving energy changes, the sign is important. So a minus sign indicates that it's exothermic, and a positive sign indicates it's an endothermic reaction. On to question 3. Hydrocarbon is a very standard definition. It's made up of 2 words, hydrogen and carbon. So a hydrocarbon is a substance made up of hydrogen and carbon only. The general formula for alkenes is CnH2n. But1 and but2ene are obviously alkenes because they end in ene. The but tells us that there are 4 carbons present. So we'll draw the 4 carbons. But1ene, the 1, then tells me that the double bond is attached to carbon number 1. Now I can do it at this carbon and number it 1, 2, 3, 4. Or I could have put it here and numbered it 1, 2, 3, 4. Because if I put it here, it's just the same as this molecule, only flipped the other way around. Remember, carbons have 4 bonds, so I need to then complete this. Now, well, this carbon has already got 2 bonds, so it needs another 2 bonds. So I'll put 2 hydrogens there. This carbon has 3 bonds, needs another one. Again, I can put it down or above the carbon, doesn't matter. I need to put another 2 hydrogens there and 3 here. Butene, again, is made up of 4 carbons. This time the double bond is attached to carbon number 2. So if I number it here, 1, 2, the double bonds here. Again, I need to make sure that all of the carbons have 4 bonds. So I'll put 3 there, 1 there, 1 there, because now you can see this carbon has 1, 2, 3, 4. This carbon is 1, 2, 3, 4. Again, these hydrogens could be up here, but it doesn't matter. And the end carbon needs 3 hydrogens. Part 2 then is the complete combustion of but1ene. Well, butene has 4 carbons, and the general formula for an alkene is CnH2n. So if n equals 4, that means that there are 8 hydrogens. So it's going to burn an oxygen, and all hydrocarbons burn completely to give carbon dioxide and water. Now to balance it, I'll start off by looking at the carbons. There are 4 carbons here, so I put a 4 in front of the CO2. there are 8 hydrogens on the left, so I need to make 8 over on the right. So I can do that by putting a 4 in front of it. The last thing I balance are the oxygens. So on the left, there are 8 plus 4 is 12, so I need 12 over here, and I achieve that by putting a 6 in front of it. So that's how you balance those equations. Start off with the carbons, then do the hydrogens, and finish with the oxygens. Of course, if it had been incomplete combustion, then carbon monoxide and water would have been obtained. Okay, on to C, a balanced equation for the cracking of C7H16. So cracking is the breaking down of a long chain molecule into smaller, shorter chain molecules and an alkene. So if I start off and just put in the molecule to start with, and I know that that's going to break down, and one of the products is propane, because I'm told that in the question. Now propane has 3 carbons, it's an alkene, so that means it's C3H6. Now both sides of an equation have to balance. So if there are 7 carbons on the left, there have to be a total of 7 carbons on the right. Well, I've already got 3, so that means there must be 4 carbons left over. And I'll do the same sort of thing with the hydrogens. There's 16 on the left. I've already got 6 on the right hand side. If we're to balance the hydrogens, this must be 10. And then naming this product, this one here, because this is propane. Well, this is the general formula CnH2n plus 2. So if n equals 4, then 2n is 8 plus 2 is 10. This is a general formula for an alkane. Got 4 carbons, so it's going to start off with bute. And if it's an alkane, it'll end in ane. So this is butane. Part 3, why are high temperatures required for cracking reactions? Well, any time high temperatures are required, it means that the bonds must be very strong. Now the bonds in this chemical, which is actually heptane, although you don't need to know that, contains covalent bonds between the atoms, and covalent bonds are very strong. Part D, alkenes undergo addition, polymerization. That's where the alkene molecules or monomers join together to form one long chain molecule. And part 2, well, you can see that this is based on ethene, which has this shape and is surrounded with hydrogens. So that's ethene. Now, when that becomes a polymer, the double bond breaks and it becomes polyethene. So we've got polyethene. Originally it was ethene, because the poly bit means many ethene molecules together. So this time we're going from poly just to the individual alkene. Well, when we replace one of the hydrogens with a chlorine, it's polychloroethene. So working our way backwards, I then replace one of those hydrogens with a chlorine. This then becomes chloroethene. Part 3, the polymerization of ethene, and this is an equation. Just move that up a bit. So we've got ethene, that's C2H4, and we're going to have n number of those. The double bond breaks And then we want to show that this molecule continues either side of the carbons. So we show the bonds and we put brackets around it. And make sure the bonds go through the brackets. We then need to put an N outside the brackets and we put it down low, like a subscript, not up here. And that's the equation for 3 marks. And it becomes part E. Then we have to describe the chemical test for the functional group in alkenes. Well, that functional group is the carbon-carbon double bond. So that, or you could say carbon-carbon double bond. The chemical test for that double bond is bromine water. And I was going to put in and shake, because normally you have to shake or mix the bromine water with the alkene. Now it's orange to start with, or you can say brown. And it's going to change from orange or brown to colourless. And that colour change only happens with alkenes. So that tells us there's a carbon-carbon double bond present. The other thing we have to do is write a balanced assembly equation for this reaction. Well, the alkene is ethene, which is C2H4. And that's going to react with the bromine, which is Br2. Because if I do it over here, the bromine adds across this double bond. So that bond breaks, and then the bromines add there and there. So the whole molecule of bromine adds across that double bond. So we end up with C2H4 Br2. Question 4. Then we have to calculate the concentration of calcium hydroxide. Now we've been given the volume of the calcium hydroxide is 25.0. You've got to be careful that we put the right numbers or values with the correct substance. So the volume is 25, and then the nitric acid, the volume is 24.0. That was the average titer. And the concentration is 0.75. So you can see now that we've got 2 values for the nitric acid. That means we can work out the third value, which is moles. We only have 1 value for the calcium hydroxide, so we've got to work out the number of moles of nitric acid first of all. Well, the number of moles is concentration times volume, and we're going to divide that by 1,000. We've got to turn cubic centimetres, the volume, into cubic decimeters. So I can do 0.75 times 24 over 1,000, or I could have done 0.75 times 0.024, and then I wouldn't have had to divide that by 1,000 again. So that works out to be 0.018 moles. Once we've got the moles, we can look at the ratio to determine the number of moles of the calcium hydroxide, and you can see from the equation that it's a 2-to-1 ratio. So that means that the moles of calcium hydroxide is 0.018 divided by 2, which is 0.009. Now we have the number of moles, calcium hydroxide. We know the volume, that is the average titer. That means we can determine the concentration. So concentration equals moles divided by volume. So again, we can divide by 0.0025, or we can divide it by the volume, which is 25, and then times it by 1,000. So again, it doesn't matter what you do. And that gives us an answer of 0.36 moles per cubic decimeter. Part 2 then requires us to calculate the concentration in grams per cubic decimeter. Well, if you think of what this is, moles per cubic decimeter, well, to work out moles, it's the mass over the MR. This question requires us to work out the mass. So that's going to be the moles times the MR. So work out the MR of calcium hydroxide, 74. And then the concentration in grams per cubic decimeter is going to be 0.36, because that's how many moles there are per cubic decimeter. 0.36 times the MR. And that gives an answer of 26.6 or 26.64 grams per cubic decimeter. Part B then we'll have to calculate the total volume of gas. Now be careful here, because it's the total volume of gas of NO2 and O2. Now anytime you're calculating a volume of gas, you're going to be using 24 if it's in cubic decimeters, or 24,000 if it's in cubic centimeters. It's cubic decimeters, so at some stage then we're going to have to use the value of 24. Now I can see in the right hand side that there is a total of 5 moles of gas. So there are 4 moles of the NO2, the nitrogen dioxide, and 1 mole of the oxygen. And that obviously gives a total of 5 moles of gas. So we've got 32.8 kilograms of calcium nitrate. I've got to work out the number of moles of calcium nitrate. So I'm going to convert this to grams. Remember, when you're working out moles, the mass always has to be in grams. So that's going to be 32,800. I'm going to divide that by the MR of calcium nitrate, which is 164. And that equals 200 moles. Now remember, the total moles of gas is 5. I could work out the moles, or the volume produced here and the volume produced here, and add them together, but I don't need to do that. So all I have to do is use the ratio. So I know there are 200 moles here, and I can see it's a 2 to 5 ratio. It's going to be 200 divided by 2 times 5. And that means there are 500 moles of gas in total. I can now convert that to a volume. So it's going to be 500 times, and this is where the 24 comes in. And because it's 24 cubic decimeters, the answer is in cubic decimeters. Avogadro's law states that equal volumes of gases contain the same number of particles under the same conditions of temperature and pressure. Definition you just have to learn. Now, using Avogadro's law is actually quite easy, because if we have 160 cubic decimeters of gas, we can just say it's the ratio of 1 to 2. So all we need to do is multiply the 160 by 2. And that's the answer, 320 cubic decimeters. Question 5 is about electrolysis, and this is when an electrolyte decomposes using electricity. And the key words there are decomposes and electricity. The electrodes are made from graphite. You could have platinum as well. Platinum's an expensive metal, so graphite is used where possible. 2 reasons why graphite is used. Oh, and by the way, don't say carbon. So it's an allotrope of carbon that's used, which is graphite. 2 reasons then why graphite is used. Very simply, 1, it's a good conductor of electricity, and don't just say good conductor, you must have electricity in there. And the second reason is that it's inert or unreactive. In other words, it doesn't actually take part in the reaction itself. Now, why would this need to be carried out in a fume cupboard? Well, remember, we're electrolyzing or breaking down, decomposing lead to bromide. And bromine is going to be formed in this reaction. And bromine is a very corrosive or toxic material. You could also say lead is toxic because, of course, it is. So anytime you're dealing with halogens, the bromine, chlorine, fume cupboards tend to be used just because of the toxicity of the elements. The positive electrode is known as the anode. So on to C, then the observations. I'm just going to draw out the 2 electrodes. So we've got our anode and cathode. The lead 2 ions, because remember this lead 2 bromide gets split into lead 2 and bromide ions. So the lead 2 is positively charged, it's going to be attracted towards the electrode. And that's why you get a grey liquid formed here, lead. So at the negative electrode, you have lead. And the half equation which shows the formation of lead is Pb2 plus, which gains 2 electrons. And remember, half equations always contain E minus. And then it forms lead atoms. At the anode, bromide ions migrate towards it. And they each give up an electron. The 2 bromine atoms then combine to form bromine gas. And bromine gas is a red-brown colour. So we've answered then the next part. The electrolysis product is bromine. And the half equation is going to be Br minus goes to give a bromine atom, and it releases or produces that electron. Another bromide ion is attracted to the anode. It does exactly the same thing. And then those 2 atoms join to give you bromine, a bromine molecule, which is Br2. So a total of 2 bromide ions, which lose a total of 2 electrons. Now do just be careful here that you don't write 2Br, because 2Br means 2 separate bromine atoms, whereas Br2 means the atoms are covalently bonded together. One other thing is that you can put the electrons on the left hand side. So for example, you could have 2Br minus 2 electrons goes to give Br2. But it's normally written the way I have it here in the table. On to 6, decomposition, which is the breaking down of a substance of hydrogen peroxide. Well, hydrogen peroxide is H2O2, and it decomposes into water and oxygen. And of course, it needs to be balanced. The catalyst is manganese dioxide or manganese 4 oxide, which has the formula of MnO2. The test for oxygen gas is that a glowing splint relights. And we're on to the last part, part B. So oxygen reacts with both metals and non-metals to form oxides. Complete this table. Well, metal oxides form bases. And if those bases dissolve in water, they'll form alkalis. Non-metal oxides form acidic oxides. So that will help us in answer this question. Magnesium burns with a white light, a white flame, not a glow, it is an actual flame. The appearance after the reaction is finished is that you'll be left with a white solid or a white powder or a white ash. And then the nature of the oxide, well, that's what I've done up here. Magnesium's a metal, so the metal oxide, the magnesium oxide, is going to be basic. Sulfur dioxide then, when it burns, well, it's a yellow solid, so that will melt. It burns with a blue flame. Gives off a pungent smell, which you could say as well. It forms a red liquid. You just need 2 things here. So yellow solid melts, blue flame is fine for 2 marks, but as I say, you could also go on to say there's a pungent smell or a red liquid is formed. The product that's formed when sulfur burns with oxygen is a colourless gas. Now it can form a misty gas once it reacts with the moisture in the air, but the gas itself, the dry gas, is colourless. And then the nature of the oxide formed, again, if we look up at the top, non-metal oxides form acidic substances. So sulfur dioxide is going to be acidic.